Hello everyone, today in this video we'll be discussing the fourth module of OS, which is related to memory management. And this module is divided into two topics, which is memory management and virtual memory management. Okay, and under these the subtopics are also present, so we'll be discussing all of them each one by one. And before starting, please do like and subscribe to my channel. It helps me make more videos like this. And if you watch this video till the end, easily you can score more than 80% marks. We'll be discussing all the important concepts you need to know from the exam point of view. So without wasting more time, let's get started. First, let me change the pen to the pointer. Okay. So now, first we'll be discussing the memory management. Okay, what all the things you need to know from the topic memory management. So we have first memory management strategy. So what do you mean by memory management? See, the term memory management means that when we perform some operation. Okay, so once our operation is performed, at that time we require a process to be executed, and that process needs some memory. Okay, so we cannot allocate all the process at the same time. So we need to replace some process and do the management, which process is actually required in the memory and what data is needed. All those things we need to do it one by one. Okay, so that is what is called the memory management. Okay, we'll be seeing how we will be performing the memory management in this module. Okay, so the program and the data must be brought to the memory from the disk. Okay, disk will be having the data, we have to bring it to the memory. Every process has a memory space. Okay, all the processes which are present, it will be stored in the memory space. The address of the memory space is denoted by base and limit register. Base is the register which will be starting address point, and limit register will be the one which will be having how much it is occupying. Okay, so we have some concepts here, like for example, the first one is the address binding. So whenever a process is brought into the memory, it is brought into the memory, we'll have to store that process in between some space. That is called as the address of the memory. Here we will be having the address binding, which is allocating the address to the process. It happens in three stages. If we do it at the compile time, it is called the it is known as address binding at the compile time. We can do it at the load time also, when the program is loading, or we can do it during the execution time. Okay, and we have the logical and the physical address space. You need to understand the difference. Physical address space is the actual address of the process in the memory. Okay, in the main memory we will be having an address that is called as the actual address, that is physical address. Logical address is the fake name given to the physical address. For example, if logical address is 346 and relocation register has 14,000 here, how do we calculate the physical address? Is that 346 plus 14,000, this is the actual address. Okay, so in order to store this large address, we need more space, so we'll be using a logical address here, which will be the relative address to the relocation register. Okay, so these are the two different types of address. Physical address is the actual address, and logical address is the fake address. Okay. Next is the dynamic loading. Okay, what do you mean by dynamic loading? See, the process whatever is required. Okay, see, if there are n number of processes are present here, but I require only few of them. Okay, so what I will do is I will just load only few of them whenever I am requiring it. I'll not load all the process and keep. Okay, that is called as dynamic loading. Loading the stuff only when it is needed during the runtime is called dynamic loading. And we also have dynamic linking, which is used to link to a library without actually copy pasting all the code to the local system. So library is the place where we'll be having all the actual codes, and we are linking it to the library so that we are using it without actually loading it. That is called as dynamic linking. Also, we can use shared libraries to save some space. This is a library, it is shared between two processes. We need not have this copy here and here, only one is sufficient. That will also save space. Okay, moving to the next topic, which is swapping. A process can execute only when it is present into the memory. That's common sense. If this is a memory, and the process will execute if only if it is present inside the memory. If it is not present in the memory, the process does not exist. If any other process wants to execute while the current process is getting executed, it gets swapped to backstore. Okay, what happens is P1 is getting executed. If P2 wants to execute, P1 will be gone to the backstore, it is another place, and P2 will be executed here. When P2 is done, P2 will go to backspace, P1 will resume execution. This is based on the priority. If P1 is more important, it will be continued. If it is not more important than P2, it will be swapped, and P2 with a higher priority will be given the chance to execute. Disadvantage is that context switching time is high. In order to switch P1 to here and then again bring back here the P2, that time is more. That's only the disadvantage of swapping. Moving to the next topic, we have contiguous memory allocation. It's a very important concept. So what do you mean by contiguous memory allocation? Memory is divided into two parts. Two types of memory are there. First is the memory for the OS. Second is the memory for the user. Each process is contained in a single contiguous section of the memory. So every process which is present, that will be in a single contiguous section of the memory. So I cannot have a half process here and half process somewhere else. I should have the whole process in a continuous memory allocation. Contiguous means continuous. Okay, so to ensure that, we'll have some rules here. First is memory mapping and protection. We have to have a memory mapping technique to map which memory is present where. Okay, and memory protection means protecting from alteration of the data. Okay, we also use memory management unit to manage those memories. Logical address is mapped to the physical address. And memory allocation, there are two types of memory allocation: fixed size and variable size. Fixed size means the whole memory is divided into fixed size of blocks, and those blocks will be used as the places to put the process inside there. Variable size means it is not fixed, it can be divided as much as it is required based on the process requirement. That is variable size. Okay, suppose that in variable size we have different kinds of data present here, so different spaces will be there, different sizes of empty spaces will be there. Now, three strategies to select a hole from available holes. Hole is nothing but an empty space. Now I want to execute a process, I want a particular size of space. Okay, so suppose that I want 10 MB space. Okay, so I have to search 10 MB from the available how many spaces are there. Okay, so I can use three strategies. The first one is first fit. Okay, so I'll be checking all the available spaces here, and whichever space I get first as okay, like for example more than 10 MB I get, that I will take. The first hole big enough I'll be considering. Second is best fit, the smallest hole big enough. Okay, I'll be searching the entire available space, and I'll be selecting that hole which is the least required for my purpose. For example, there are three holes present. First is 12, second is 11, and third is 17. If I use first fit, 12 will come, I'll use 12 because I only need. But in the best fit, what will happen, I will be searching all and I'll be choosing 11 because this is the least one which I am required, right? From 10 I required the least one, it is 11 than 12 or 17, right? So that is the best fit. Worst fit means biggest hole, it will select 17. That is the worst scenario. Okay, it is not required, it will be waste of space. Okay, another concept is fragmentation. There are two types of memory fragmentation. What do you mean by fragmentation? See, this whole memory is divided into different spaces. This is one space, this is another space, this is another space. These are all different blocks. Okay, and the shaded part is the one in which the process has used this much memory. In this block has used this much memory, in this block this much memory, in this block it has used this much only. So the empty spaces remaining after the process has used the block, that is called as internal fragmentation. These empty spaces are not usable, right? Because the process requires a free block, it half from here and so on, it needs a full block. So these spaces are being wasted. That this concept is called as internal fragmentation. External fragmentation is when free block space is not contiguous, means this is also similar to internal fragmentation but at a higher level. Okay, so here these spaces needs to be used. We can use that by using two methods. First is compaction. Compaction means push all this into the left side so that a big space will be made here, and this can be used for another process, that is compaction. Second is use non-contiguous memory, means take these memories from here and map it virtually like an imagination as a big space. Okay, that is called as use non-contiguous memory. Two methods are there, paging and very important concepts. We'll discuss the physical frames. The physical memory is present, if it is broken down into different blocks, each is called as a frame. Okay, and if it is the logical memory which is broken down into the different blocks, it is called as a page. Okay, so address CPU is generated by page number and offset. Okay, the page number is present here and offset is present here, means in this page how much more I have to go to reach the destination. Okay, from page I will map to the frame, from frame I'll get the So page is mapped to frame and frame is mapped to the physical address. So seeing this diagram will make the things more clear. This is the logical memory which we have. The pages are stored here, and these pages are not contiguous. It is non-contiguous, but it is looking like contiguous, right? How it happens is it is mapped to the page table. Page table has the actual physical addresses present here. Okay, so it will be 1, 4, 3, and 7. This is the page table, and the logical addresses are given from 0 to 3, and the physical memory is mapped here. The actual address is present 1, 3, 4, and 7. Okay, so this is how the logical mapping happens, and this is the concept of paging. We'll be storing the pages as if it's a contiguous memory, but it will be non-contiguous. Okay, moving on to the next one, which is translation look aside buffer. It is a special small and fast lookup cache. It is called as TLB. It has two parts, key and value. Okay, the TLB is just a table where we'll be having a key as well as the values associated with that. Now what is the key and what is the value? When logical address is generated, the first TLB is checked. When logical address is generated means for a new address, when we have, we'll be first checking the translation look aside buffer. It's the cache memory for the logical address to the physical address mapping. Okay, first whenever we want to check what is the physical memory for the logical address, we'll be having to look directly. We can look directly, but also to save our time, if the same logical address comes twice, we can save that in a translation buffer, and we can use the translation buffer to get the physical address more quickly. Okay, that is called as translation look aside buffer. Here also the concept of protection comes, protecting the data from getting the overwritten or wrong data to be written. That is called as protecting the data. So we use two bits here, the valid and invalid bit. The valid bit indicates that the page is legal, invalid bit indicates that the page is illegal and is to be removed. What do you mean by a page illegal or legal? Legal means it is present inside the page table, and illegal means it is not present inside the page table and it has to be fetched from the main memory. Okay, so for the protection we'll be using the following bits. Next we have the sharing pages. What do you mean by sharing pages? Two or more processes are there, those are referring to the same data which is present here. That is called as a sharing pages. Okay, if the editing takes place, it will happen on copy page. Okay, so suppose that I edited one of the data which is present here, the edit the edit will not happen in the same page. A copy of it will be generated and the editing will be happening on the copy of it. Okay, so this is called as copy on write and will be discussed in detail later. Moving on to the next one, which is the structure of the page table. Okay, so there are three techniques of structuring the page table: the hierarchical paging, hashed page table, and inverted table. Hierarchical paging will be having different levels. Okay, so the pages is indexed in different levels, means this will be having one range, and from this range to this range there will be more expansion present here. Okay, so this kind of paging is called hierarchical paging. Okay, and for locating an inner page, means the last level of page, we'll have to use the page number and page offset. So this is an example of page number and page offset. Here will be having the page number 72, means in the first level you have to take the 72, in the second level you have to take the 34, and inside 34 go 16 more sections and you will be reaching your destination. That is called as the hierarchical paging. Second one is hash page tables. So it is used to handle the address spaces larger than 32 bits. If it is the having space, the address space more than 32 bits, we'll be using the hashed page tables. Now what is a hash value? Hash value is generated after putting the input and performing some operation. We'll be getting an output. That output is called as a hash value, and this hash value is used to refer as a virtual page number, and this value will be acting as an index. Okay, so it has three elements. The each element has three fields: virtual page number, and the mapped frame, and the pointer to the next element. So for one hash value there can be multiple elements present. Okay, so that is what the hash page table looks like. Okay, so the working of it will be as follows: virtual page number is hashed to the hash table. So inside the hash table the virtual page number is present. It is compared with the first element. That virtual page number is compared to the first element which is present. If it is the element which you are looking for, we'll take it, else we'll go to the next one which is pointed by the previous element. Okay, so see the second data type is mapped, I mean the third data type is pointed to the next element. So if first element is not there, it will point to another element here, which will be we'll be checking that. If it is not, it might point to the third element, and we'll go till the end. If we don't get, it is not present inside the table. If we get, will be returning that. Okay, this is how it works. The last one is the inverted page table. So each virtual address consists of a triplet. Okay, each virtual address consists what? A triplet: process ID, page number, and offset. Okay, and each inverted page entry consists of a pair: process ID and page number. Okay, it consists process ID and it consists page number. Now see, here the CPU is present here and it passes three things: page id and page and offset. Now the offset will be taken and put here, and inverted value, how we will get that? How much far it is from the beginning, the pid, how much far it is from the beginning, that is the I value. That I value will be taken. In combination of these two, we can easily find the physical address in the physical memory. Okay, this is the third type of uh, structure of the page table, which is inverted page table. Moving on to the next topic, which is segmentation. A logical address space is a collection of segments. Okay, it has a lot of segments present. Okay, and each segment has a name and the length. Means, see, this is the space here, and a lot of blocks are present here. Each of these blocks is called what? It is called segment. It might be the memory, it might be the process happening, it might be the variables, it might be the resources present, it might be the time. So whatever the values we are using inside the program, that all is stored inside a big space, and each of them is called as a segment. It has name and its length. Okay, and segment table is present, which will have the base address and the limit, means how much range it has. Okay, means the process range, what it is, means how much is the size of the process. Okay, together these values are pointing to a physical address. Now there is a segment number and an offset within the limit that maps to the physical address. Segment number and the offset both map to the physical address together. Okay, if it is out of limit, then OS goes into the trap state. Now see, I told you that offset is within a limit. Suppose that I got offset which is more than the limit. Suppose limit is 100, I got an offset which is 200. Now along with segment number, suppose that it is 16, 16 and 200 does not exist. So if it tries to find out that, it will go into the trap state. Okay, that is the concept behind segmentation. Moving to the second half, which is virtual memory management. Now what is virtual memory management? Virtual means imagination. Okay, now it allows for execution of partially loaded process. Okay, if a process is not loaded fully, virtual memory will be helping us to execute that. How does that happen? Let's have a look. The virtual memory captures all the free spaces and keeps together. Okay, so in the main memory there are many free spaces here and there. All those will be captured and put together. That is the virtual memory, and it will have its own address, which is logical address. Okay, so these pages will be mapped to the memory map, and that will be pointed to the actual physical memory. Okay, so memory map acts as an interface and a map between the virtual memory and the physical memory. So based on this map, we can connect the pages wherever it is present to which actual location it is present in the main memory. Okay, that is how the virtual memory works. Now this process allows files and memory to be shared by several process through page sharing. Okay, so it will just have one single space where the memory is present here and the page is present here, and that will be used by the multiple process, so it saves space. Okay, and virtual memory is implemented using demand paging. Now what is demand paging? Let's have a look at demand paging. Demand paging means page is swapped or taken from the memory on demand. Whenever page is required, then only it will be taken from the memory. Everything will not be taken from the memory. It will be leading to lesser IO operations, and lesser memory will be consumed. It will be more faster. Valid and invalid bit is used to denote the pages, if it is in the disk or it's in the memory. Suppose that a page is invalid. What does that mean? It means it is a trap and page needs to be brought from the memory. If it is invalid, means the page is not present inside the virtual memory, it has to be fetched from the main memory. Okay, that's what the page invalid means. If it is valid, means it is already present in the virtual memory, you can use it. Okay, so the following diagram shows the steps in page fault handling. Okay, so suppose that I want to fetch a page from the main memory. In case it is invalid page, means if the page is not present inside the virtual memory, I have to fetch it from the main memory, right? So in that case, I'll be doing the page fault handling. Let's have a look, how does that happen. So this is the diagram. First what happens? First the process requires a page. Okay, process requires a page. So it will check the page table if that page is present or not. Okay, there are two options. There are two possibilities. Page is present here in the page table. It is not present here. If it is present, it will return and go to the process. If it is not present, it will go to a trap state in the OS, and OS will fetch from the main memory, and it will be loaded into the physical memory. From the physical memory, it will be loaded to the page table, and then the instruction will be restarted, so that from the page table the page is taken into the main process. Okay, moving on to the next one, which is copy on write. Here what happens, it creates a copy when the page is edited. Okay, so here is an example of process 1 and process 2, and here is the physical memory. In physical memory the pages are present, and process 1 and process 2 are referring to these pages. Now what happens is, if process 1 wants to edit any of the page, okay, suppose that it edits the page C and writes some other content here, what happens, it will not be written into this same page. Why? Because if it is written to the same page, the process 2 will be able to look at the edited content and not the original content. So what happens, a copy of page C will be created and the edit will be happening there, and the process 1 will be editing that. Okay, and the original one will be retained. That is called as copy on write. Moving on to the next one, which we have the page replacement. Page is to be replaced when new page comes. Okay, whenever a new page comes and the memory is full, we have to replace the older pages, right? So we'll be using the page replacement algorithms. For that, we'll be denoting using modified or dirty bit. It denotes page was modified or not. If the page was not modified, we can replace it because it was as such, and we can put a new page on the same space. And in case if it was modified, we cannot overwrite because the modified one needs to be saved first in memory. In that case, what happens, changes are written to the memory, then the replacement happens. So to do this more effectively, we'll be using a page replacement algorithm. There are three important algorithms. We'll be discussing each one by one. First one is FIFO. FIFO means first in first out. Okay, so see here what happens. In this algorithm, the first page in will be replaced first when the memory is full. Okay, so suppose that the page are coming here. First page is 7, second is 0, 1, 2, 0, 3, 0, and 4. And here we have the memory space as 3 pages can be stored at once in the cache memory. So first 7 will come, it is empty, it will get stored. 0 will come, it will get stored after 7. 1 will come, it will get stored after 0. Now 7, 0, 1 is present. Now 2 also came. Now to put 2 in this space, how will I put in, will I replace 7, will I replace 0, will I replace 1? According to FIFO algorithm, first in first out. In this 3, which was first in? First in was 7, so 7 will be replaced with 2. Now it is 2, 0, 1. Now again 0 came, 0 was already there, I will not do anything. Then 3 came. Now from 2, 0, and 1, now 3 came, I have to replace either 2 or 0 or 1, I have to replace. Now whether 2 came first or 0 came first or 1 came first. Accordingly, first 0 came. It has repeated here, but we'll not consider that. First which it came. First came 0, right? So we'll be replacing 0 and putting 3 here. Then whichever next comes, we'll be replacing 1 here and putting 0 here. Next one will be replace 0. After that, 2 is the means oldest one, right? In 2, 3, and 0, 2 is the oldest one. We'll be replacing 2 with 4. Okay, now 0 came means this is the new thing we are writing, and 0 will be considered from here and not from here. Okay, once it is overwritten, we'll be considering that. Means different thing overwrites 0. That is a different scenario. This was 0 is writing over 0 only. Okay, so that's why we did not consider here, but here we'll consider this 0 because it is overwriting an other number, not the same number. Okay, so in this case 2 is oldest, 2 is here, so we'll replace 2 with 4. This is the FIFO algorithm. Now in FIFO's algorithm, what happens is Bilady's anomaly. What does that mean is, more frames means more page fault. What is page fault? Page fault means, suppose I wanted number 3, okay, but 3 is not already present here, I have to replace something, that is called as a page fault. In case of 0, 0 is already present here, will not be replacing 0, will be using the same 0, that is not a page fault. Okay, got the difference. Now more frames means more page fault. This is what Bilady's anomaly suggests. So to overcome that, we'll be using the optimal algorithm. Now what does optimal algorithm do? Replace the page that is not that will not be used for the longest period of time. Okay, we'll replace that page which will not be used for longest period of time in the future. So it requires knowing the reference string in advance. Means this whole string I need to know to get to check that which one will not be used for longest time. Okay, let's understand this using an example. See, 7 is present here, I'll put 7. 0 came, I'll put 0. 1 came, I'll put 1 here. Now 2 came here. Which one I'll replace? 7, 0, or 1? What I will check is, in the long run, which is the least used. Means 7 is used where, next 7 is used here. 0 is used where, 0 is used here only. 1 is used where, 1 is used here. So among these three, which is the last used? Last used is 7, so that one I'll replace. Okay, I'll put 2 here. Now again 2, 0, 1 present. 0 already, 0 is present. 3, when 3 came, I'll check if 2 is used least, 0 is used least, or 1 is used least. Now accordingly, 2, where is 2 coming? Here. 0, where is 0 coming? 0 is coming here. 1, where is 1 coming? Here. Least uses this one, I'll replace 1 with 3. Like that I'll keep on continuing until I reach the end of the reference string. Okay, in this way, when we do, this is called as optimal algorithm. Okay, the last one is LRU, which is least recently used algorithm. Here the least recently used page is replaced. Let's understand this using an example. 701203004. Now 7 came, I put 7 here. 0 came, I put 0 here. 1 came, I put 1 here. Now 2 came, which one I'll replace? 7, 0 or 1? I will check which one was least used. Means 1 is used recently, 0 is also used recently, 7 was used at the last, so I'll replace 7. I'll put 2 here. Now 2, 0, 1. Again 0 came here, 0 is already present here. 3 came, which I'll replace? 2, 0 or 1. Now 2 is used where? Here. 0 is used where? Here. 1 is used here. So which is the least used? The least used is 1, so I'll replace 1 with 3. Now after that 0, 0 is already present. 4 came, I have to replace 2, 0 or 3. Which one I'll replace? Where is 2 coming? 2 is coming here. 0 I have used recently, very recently. 3 is coming here. Least one is 2. I'll replace 2 with 4. Okay, so this is the least used, recently used algorithm. Moving on to the next topic, we have allocation of frames. Okay, there are two ways to allocate frames. See, frames are present and these frames are to be allocated to a process. For this is for P1, this is for P2 and so on. How we will allocate these frames? How many frames are to be given to the process? There are two ways. First is equal allocation. If m frames are there and n processes are there, then each process will get m by n frames. Divide it among all the process and allocate whatever the answer comes to every process. Second is the proportional allocation. Proportional allocation will use this formula m into si by s for each process. What is m? M is the free frames available in the system. How many free frames are available? That is m. Si means size of process I, how much size is there for the process I, and s is the total free size, total free space available. And here it is the si for the process I, how much is to be allocated, the size of that process is present here, and m is the number of free frames available. Now whatever answer I get, that many frames will be allocated to the process I. Okay, moving on to the last topic, which is thrashing. What do you mean by thrashing? A process is thrashing if it is spending more time paging than executing. Paging, which you already discussed what it means, fetching from the memory the values and keeping it into the page table, that is called as paging. Now if the paging is happening more than executing the process, it is called as thrashing. Now how does thrashing happen? The cause of thrashing, mainly it is increasing the degree of multiprogramming, putting more and more programs into the same system. After a point it will become more, it will backfire, and the process utilization of CPU will become less and thrashing will become more. As more and more program comes, the more pages are required to store them. So what happens? The thrashing will happen. It spends more time handling the paging than actually continuing the execution. So it leads to more paging and reduces the output, which further leads to more paging and it continues. Okay, so what is the solution to thrashing? Working set model is an algorithm which is used to determine how many pages are required so that thrashing will be avoided. By using the working set model, we'll be able to determine how many pages are required so that we'll not come to this point, we'll stay at this point only. Okay, that is calculated by working set model. Okay, so that's all for this video, and if you found this video helpful, please do like and subscribe. That helps me make more videos like this, and thank you so much for watching. I'll see you in the next